Hello, everyone. This is Professor Ma, and this is the sections on improper integrals. And basically, there are three topics we'll cover. It's one of what we mean by improper integrals. And basically, there are integrals over improper domain. Now, what do I mean by improper domains? The improper domains are where the function is not exactly defined, like boundaries of functions. Improper domains, I mean, like functions that from say one to infinity. Okay, so that's we consider as improper domain because before integrals like 1 to 2 is over closed domain. Now we have this domain that's go to infinity. So that's an improper domain. Another type of improper domain is like for the function 1/x, and then as the function get close to 0, it goes up to infinity. So the interval 0, 1, we will consider this as an improper domain. Okay, because the behavior of the functions it shoots up to infinity at a boundary point. Okay, so this type of line infinity here 0, 1, these are called improper domains. And we're going to address then, of course, the integral of that. And then we're going to talk about convergence or divergence, meaning whether the integral is finite or infinity. And we're going to talk about basic theorems, then how do we justify something, even though a lot of cases we cannot integrate it, but how do we justify that the integral, improper integral, is finite, or the improper integral has to be infinite, converge or diverge, okay? And then finally, for concrete problems, it turns out the function 1/x serves as a boundary for two classes of improper integral. So let's get it started. Um, so here we have integral go from 0 to infinity, e to the minus x, and basically we try to calculate the area underneath e to the minus x from 0 all the way to infinity. Okay, so we don't really have an integral that antiderivative and plugging the limits of the boundary. So we call this type of integral improper. Similarly, as we said before, if the boundary point, the function goes to infinity along the boundary points, we call this type of integration improper also. And then we might have combination of both types where it goes to infinities. The domain goes to infinity, and you have spikes that goes like asymptotes, and we're integrating around that. Okay, so all these types are integral. We call them improper integrals. Okay, so these are two prime examples. One has an infinite domain, and the other one in the domains it shoots to infinity. And how do we define? It's easy. We define as limit. So by going to infinity in the limit of integration, we mean that we substitute the upper bound by any number u, then we let u go to infinity after we integrate. So pass the limit problems to the antiderivative. Okay, and so this will works nicely. So for example, we calculate the antiderivative minus e to the minus x. And what do you mean by infinity? Basically means plugging infinity is going to become 0. Okay, but to say a little bit more carefully, is x goes to infinity, you let the limit, you calculate that. Okay, so that's how we calculate. So therefore, this improper integral converges because the answer is finite. And also, we're going to look at all the examples. We're going to look at positives, function of positives. Okay, about convergence and divergence. And similarly, we have like I just said that. I mean, here's diverging examples. Okay, and if we limit the function to cosine x, and then we're going to take the antiderivative, and here's the lower limits. It's going to go to minus infinity. Except the limit, of course, as x goes to minus infinity, sine of x doesn't exist. This one is 1, 0. This one undulates. So the limit doesn't exist. So this, in particular, the improper integral doesn't exist. And if you look at cosine go up and down like that. If you try to think about how much area is under here, sine area, it's really not well defined from here to all the way to infinity, right? From minus infinity up to this point. So therefore, we say that it's undefined. And so here's an example where when x goes to 0, on the boundary 0, it shoots up to infinity. Okay, so we converted this improper integral as a limit. Okay, and also I want to point out this x to a power, and we compare to the function 1 over x. Okay, x to the 1 over x to the 1/2, which is x to the minus 1/2, is this blue line over here. Okay, it sits below this green line, and we are integrating from 0 to 1. So therefore, since the green line is bigger than is on top of the blue line, so we have integral of 1 over x dx, the 0 to 1, the improper integral. It's going to be bigger than integral of 1 over x square root dx, 0 to 1. Okay, so just want to let you note that. Okay. Later on, as we said before, that 1 over x over here is going to serve as an important boundary between convergence and divergence. In this case, because the blue line sits below the 1 over x, it turns out it's going to converge. The area is going to be finite. So I take the antiderivatives and then plug in the lower limit x approaches 0, and as x approaches 0, I get 0. And so 2 minus 0 is 2. So the blue area is 2. Now, how about underneath the green area, the 1 over x? Well, antiderivative 1 over x is log x. Now, if I take limit x go to 0 for log x, that goes to minus infinity. So the whole thing becomes positive infinity. In other words, the green area underneath this green line over here, this entire big blob, it's infinity. But the blue one that we had, okay, which one? The blue one we had before, the underneath the blue line. That's what I'm trying to do. I'm making a mess here. Okay, this shade of blue area, that's 2. That converges. Okay, that's what we mean, that you will see later on that the 1 over x actually serves as a boundary for this type of behavior. Now, the part, therefore, the x minus 1/2 improper integral from 0 to 1 converges, but the 1 over x diverges. Okay, this is what we will say. And how about from minus infinity? How about how it's improper on both ends? Then we solve this by taking limit from both ends. So for instance, if I want to integrate 1 over 1 plus x squared, it looks like it's bell shaped. Okay. and uh, its antiderivative is tangent inverse. And now I let the limits. How do I plug in infinity and minus infinity? Well, I plug in. I replace define to be u, and let u go to infinity, and then the other one I use minus u. That one goes to minus infinity. And we find out that tangent inverse of both is pi over 2 minus pi over 2. So the one that would pi. Okay, so uh, there are two principles now we're going to use to compare to draw conclusion whether a function's integral is improper integral at converges or divergent. We first have a so-called ceiling principle. Okay, I have a formula, a ceiling. Here, the ceiling refers to something on top. Okay, bigger than g of x. G of x is got trapped below it. It's kept by the ceiling. And the antiderivative of the ceiling and the definite integral of the ceiling is finite. And g of x is below this f of x. Therefore, conclude that the definite integral of omega b g must also be finite because it's underneath, it's smaller. Okay, here's a picture. I have this red area, which is under f, and it is finite. And now I know the G is below, underneath it is this black area. Therefore, I can conclude the antiderivatives of G is also finite. Notice this doesn't work if we have this, we have to have this inequality. And these, suppose I don't have this inequality, that means that G may be bigger than F. So for instance, it might be the case, and then G might be way up here. So if I put the G way up there, and look at the area underneath, G, and like all that, even though on the pictures, I know this is finite, this is like in areas less than infinity, but G on top can be, as high as can be. So I have no idea what the antiderivative of G is. Okay, so therefore, if G is bigger than F, okay, and then I really don't know anything, and F is finite. Okay, then I cannot conclude anything. In the same principle, I got a floor principle. If I'm bigger than something, and if I'm bigger than a floor, and that floor itself is infinite, or integrated, I'm bigger than that infinite floor, then we have to be, then the improper integral has to be infinity also. Okay. In other words, the area underneath the red area is more than the black area, but the black area is already infinity. So the red area must be infinity also. So the logic of these two, make sure you use it, you use it in the correct directions. Okay. The condition is being satisfied. Okay, that gives us the following observations. Okay, so we're going to look at the function 1 over x, and we're going to break up into 2 domains. And so we're going to look at the domains on these from 1 to infinity. And we'll also look at the integrals of the domains from 0 to 1. Okay, notice on both of these, because the symmetry, basically this area over there, the same as the area over here. So on the right hand side, this area over here integrated. The blue area keep going to infinity. That's infinity. Okay, the definite integral. So in the same token, the blue area integrates by infinity. Okay, so on both sides they diverge. Now, if I compare to functions of the type, which we're going to compare to function of the type x to raise the power x to the p power. Okay, and to answer the question, does this converge or diverge? Okay, depending of course on P, and then of course the other ones is for a dual from on the right hand side, 1 to infinity x to P. Does this converge or diverge? Okay, and here we go. And here's the conclusion. Okay, let's look at the right hand side. Okay, notice 1 over x. Here's 1. Okay, so y equal to 1 over x is less than 1. So the more I raise to power, it gets smaller and smaller. And in this case, it serves as a boundary for if you a power that's smaller than 1 over x below the 1, then your improper integral from 1 to infinity is finite. Okay, even though 1 over x is itself infinite. But if you, it turns out it serves as a boundary, but once you fall below that boundary as a power functions, then the integral converges. And similarly, from the improper integral from 0 to 1 is the other way around. Okay, notice here's 1 over x. Okay, and it's bigger than 1, right? So from 0 to 1, 1 over x is bigger than 1. So if I square 1 over x, then that is going to become even higher. So here's 1 over x squared. Okay. So this green line, and then over here, no, I shouldn't use green because that's 1 over x. So let me use a blue line. This blue line, 1 over x squared, will be higher than 1 over x, and then this gray line 1 over x cubed is going to even be higher. So their integral is going to be bigger than 1 over x. So therefore, between 0 and 1, the improper integral of higher power diverges. They all go to infinite because they're bigger than 1 over x. On the other hand, square 1 over square root x, 1 over cube root of x, they get lower and lower than 1 over x between 0 and 1. So they converges. In other words, they converges for p less than 1. Between 0 and 1. Between 1 and infinity, converges for p bigger than 1. So 1 over x is the boundary we compare power functions to for convergence and divergence. Okay, so this is the 2 examples you should which keep in mind. So when we need a whole lot to compare things. So for examples, and so we're going to use comparison principle to draw a conclusion about whether this formula converges or diverges. Okay, notice it's hard to integrate these. So one of the things to do is we can just drop the compare to the highest degree terms. Same tricks. Okay, hopefully that the inequality when we integrate goes in the correct direction. We can conclude something. Okay, so for here, this is a bigger number than just x to 3. What? Because of that. It's in the denominator, so therefore this fraction is smaller than this fraction. So I'm going to use ceiling theorems and see how much is the improper integral for these for 1 over x to 3 half. And unfortunately, that's finite. Okay. Hence, this is a smaller integral. It must converges also. So this is the argument. Okay. And so for next problem, okay, suppose I break up the formula into 2 parts, and I notice between 0 and 1, x is between here and here. X plus 1 is smaller than 2. Okay, this is smaller than 2. And then 2 over smaller than 2, that part is bigger than 1. Okay, so the entire product times x squared, 1 over x squared times that blue part is bigger than 1 x squared. So a lot of problems on the homework, we have to come up with these estimations or this comparison. And then from here, from this comparison, I can take the antiderivative 1 over x squared. And remember that diverges. Because between 0 and 1 over x squared is bigger. So than 1 over x. So that diverges. And my formula is bigger than this 1 over x squared. So mine must diverge also. Okay, so these are typical arguments for we're going to use for conclude things converge or diverge. Okay. Using the ceiling or the floor theorems to push it, to press it down to be convergent or push it out to be divergent. Now, what's one final note that infinite series are tied to these questions of improper integral, because I can always view a series as a step functions, multi-rule functions, between like points. If I have the series 1/2, 1/4, 1/8, 1/16, I can think of a function that's equal to, between 1 and 2 is equal to 1/2, between 2 and 3 is 1/4, 1/2, and that's 1/4, and that's 1/8, the height. And then the improper integral of f of x dx, 1 to infinity, is exactly that sum. Then I can tie in the integrals with this series. And in fact, that's how we're going to do next time. Okay. So that's it. Until next time. Okay. Bye-bye.